and welcome to a video example working through algebra and learning how to solve systems of equations using the elimination method. So again, we're trying to find the intersection. If I graph these two linear equations, where do they intersect? That point, that x and y value, is what I'm trying to find. It's also the x and y value when I put them in, when I replace both x and y with that point that I find, it makes both equations true. So elimination method, again, I'm trying to add these two equations together. Here's my steps I'm going to follow on the right. I want to get it to where I can add them together, add so that one variable turns into 0, gets eliminated, and I can solve for the other variable, and then so on and get to what the x and y should be. All right, so let's go through this and check this out. Step 1, are both equations in standard form? Are my x's lined up, my y's lined up, my constants lined up? Yep. This one's good to go. I'm in standard form. I don't need to do anything more for step 1. Step 2, this is a pretty complicated example. Step 2, I need to think about how do I get opposites. I want both the same number for x, positive or negative, to get it to eliminate, or I want the same number for y, one positive, one negative, to get them to eliminate. And you can tell I got a little bit of work in this case to get them eliminated. So what I'm going to do is I'm going to have to multiply both equations, and I'm going to target in on the x terms. I have a 3 and a 4. If I can turn them into 12 and negative 12, then I will have opposite terms that'll cancel out to 0. So what do I need to do that? Well, to get 12 and negative 12, I need to multiply the top equation by 4, and I need to multiply the bottom equation by negative 3. So I'm going to write what I'm multiplying over there, and let's just do the distributive property. 4 times 3 is going to give me 12x. 4 times the negative 10 gives me negative 40y. It's equal to, and then multiply that 4 times the 22 to 88. One big mistake I always see students make on this is they forget to multiply every term. They just multiply the term they want eliminated and forget everything else. But nope, the 3, the negative 10, and the 22 all need to be multiplied by 4. Okay, now let's do the negative 3. Negative 3 times 4 gives me negative 12x. I like that. I got opposite terms that are going to turn into 0. But now negative 3 times 6 is going to give me negative 18y. And negative 3 times negative 15 is going to give me positive 45. All right. Now, let's add these two together. There's my new system. I just multiplied, I rearranged the equations to make them a little bit more friendlier for the elimination method. And I've multiplied is done. Now let's add these equations together. 12x minus 12x gets 0. I like that. Negative 40y plus negative 18y is going to be negative 58y. Is equal to 88 plus 45. 120, 113, 133. Just double check that. Yep, 133. Okay. Well, did one variable get eliminated? Yep, my x's got eliminated. And now let's solve for what y should be. So I'm going to divide both sides by negative 58. And it looks like y should equal negative 133 divided by 58. 58 goes in 133 two times, so I could also think of that as y equals 2, negative 2. And after that, 2 times 58 is 116. So if I subtract 116 away from 33, I'm left over with 17 58s. So there we go. As a mixed number, there's my y value. Y is equal to negative 2 and 1758. You can see here why the elimination method is much friendlier than graphing, or at least gets me to a more exact answer. 1758 is a really complicated fraction, or is a really big fraction, not a nice simple one. The decimal of it's pretty ugly. If I graphed it, tried to approximate from a graph, I can maybe get close to a kind of reasonable a tenth of a decimal, but I wouldn't get this as an exact answer. This is the exact answer. But now let's look at the other steps. Normally we would back substitute and solve for the eliminated variable and then check our solution. But I'm feeling a little apprehensive because negative 2 17/58 is this huge ugly fraction. I'm not very excited about substituting that in for y and then doing the work to solve for x. Most people aren't very comfortable with fractions. So I want to show you another trick. We can actually cycle back through. So we solved for one variable. We can cycle back through, do the same steps here, but this time really multiply both equations to solve for the other variable. So let's go back through. I've got y, and now let's take another look at my system. 3x minus 10y equals 22, and then 4x plus 6y equals negative 15. Now let's look at it through the eyes of wanting to get the y values eliminated so I can solve for x. So what do I need to multiply to get my y values eliminated? Well, for 10 and 6, the least common multiple that I get into would be 30. So if I could multiply the top equation by 3 and the bottom equation by 5, I would end up with negative 30y and plus 30y. I like that, so let's do that. So distribute the 3. 3 times 3x gives me 9x. 3 times the negative 10 gives me negative 30y. And 3 times the 22 gives me 66. I multiplied that top equation by 3 on both sides just to make it a little bit bigger. It's going to work out better now. On the bottom, I'm going to multiply the 5 to get 20x plus 30y equals negative 75. All right, I've got them set up. Let's add my two equations together. This time they're going to add in a way such that my y values turn into 0. 9x plus 20x is 29x. Plus nothing plus 0 equals 66 plus negative 75. It's going to be negative 9. That's easy to solve. 29 times x equals negative 9. Let's divide both sides by 29. And x should equal negative 9/29. That's its own simplified fraction. All right, so what does my solution end up being then? Well, my two equations are going to intersect at an x value of negative 9/29. That's a small negative fraction. And a y value of negative 2/17/58. So we can find some really ugly, huge fractional intersections using the elimination method. Makes it a little bit nicer. Notice we didn't really have to do any work with fractions. I didn't have to do any adding, multiplying, or dividing with fractions. It's just I ended up at that final step dividing out to get my solution. So elimination method, we can do the elimination method. Let me say that clearly. We can do the elimination method twice, one time for each variable, knowing that I can multiply my equations to get any variable I want to eliminate out. Sometimes that makes it a little bit nicer. To check my solution, well, I don't really want to plug these back in, so I would really use a graph. And in a graph, I'll reasonably be able to tell if this point is actually the correct solution or not. All right, there you go. There's another good example of using the elimination method to find the intersection point and solve a linear system.